So welcome to this presentation. I'll take you through the process of determination of the state space model for electrical circuits. The state space model for electrical circuits. So we look at the state space model for electrical circuits. So the electrical circuits can be considered to be circuits that have RLC components. We will have RLC components, where we have the resistive, inductive, and capacitive components. The energy storage elements in this case will be the inductive and capacitive components, where the inductors will store current and capacitors store voltage. Being the energy storage elements, that means the order of the system will be determined by the number of energy storage elements in the system. If, for example, there is one inductor and two capacitors, then this will lead to 3 energy storage elements and therefore a third order system. When we model electrical circuits, it is usually common to take the initial current stored in inductors, and initial voltage stored in capacitors. So the initial currents through the inductors and initial voltages across the capacitors as our state variables. So those initial values of currents and voltages stored in inductors and capacitors respectively will be taken as our state variables. Then we will aim to write the mathematical equation of the circuits either by applying Kirchhoff's current law or the Kirchhoff's voltage law, and through that come up with the state equation and the output equation of the circuits with the initial conditions of the inductor current and capacitor voltage as the state variables. In our circuits, we can have the inputs and outputs either being voltages and currents or currents. So we're saying we can have the inputs and outputs of our circuits. So the inputs and outputs of our circuits can either be currents or voltages. So with the relevant inputs and outputs of our circuits, we'll be able to model our circuits in state space representation. I'll handle these through several examples or illustrations on how we model electrical circuits in state space representation. For example, if you have an RLC series circuit, we have an RLC series circuit represented as follows. So the circuit has a voltage source E of T as the input, then the RLC components as follows. So we have the components of the circuit as the inductor, the resistor, and capacitor. All of them are in series. So this is a series RLC network. The output is taken across the capacitor as VC of t. This is our output. This is the L, the R, and the C. We are supposed to model this circuit in state space representation with E of t being the input, and therefore can be denoted as U of t. Our VC of t, which is the output across the capacitor, is our output, and this can be denoted by our Y of t. When you have this circuit, then because all the components are in series, a current I of t, will flow in the circuit. So you have the same current flowing through the network. So for this, the same current is going to flow through the network. We can write the Kirchhoff's voltage law. So the voltage drop, that is the voltage source E of t, will be equal to the drop across the inductor plus the drop across the resistor and the drop across the capacitor, as E of t is equals to the voltage drop across the inductor plus the voltage drop across the resistor plus the voltage drop across the capacitor, which can be written as E of t will be equal to the drop across the inductor in terms of the inductor current will be L di dt. So it will be di dt plus the voltage across the resistor in terms of the resistance and current is R I of t plus the voltage drop across the capacitor, which is VC of t. We can rearrange these to form a first order differential equation in terms of the current as di dt is equals to so we take all these terms to the left and we get negative R over L I of t minus 1 over L VC of t plus 1 over L I of t. You can call this equation 1. Also, the voltage across the capacitor can be written in terms of its current, or the current through the capacitor, I of t, in terms of voltage can be written as I of t is equals to C dV dt, from which if we make dV dt the subject of the formula, we can write dVc dt is equals to 1 over C I of t, and you can call this equation 2. Then we can choose our state variables such that the state variables are the inductor current and capacitor voltages as follows. So we can take the inductor current and capacitor voltage as our state variables as follows. We can take x1 to be equal to I of t and x2 to be equal to VC of t. So we can define the two state variables as x1 to be the inductor current and x2 to be the capacitor voltage. If we do that, then equation 1 can be written as x1 derivative will be equal to negative r over L x1 minus 1 over L x2 plus 1 over L E of t. Notice this one was supposed to be E of t. So this part was supposed to be E of t, considering that this term was E of t. You can call this equation 3. And our x2 derivative from equation 2, if x2 is VCT, that means dv dt is x2 derivative, will be equal to 1 over c I of t, which is x1 of t. Then the output of the circuit is Vc of t. That means y of t, which is our output, is equals to Vc of t, which is the output, but Vc of t is x2 of t. We can call this equation 4 and this equation 5. From equations 3 and 4, we can obtain the state equation as x1 derivative, x2 derivative. These are the first derivatives of the states will be equal to, so a matrix A multiplied by the state vector x1, x2 plus a matrix B multiplied by our u of t. So for x1 derivative, it has negative r over L. So this is negative r over L. And then for x2, it's negative 1 over L. For x2 derivative, we have 1 over c for x1. So 1 over c for x1 and 0 for x2. And in terms of the out or the input, then x1 derivative is a function of the input. Remember, our input E of t is our u of t. So we'll have 1 over L, and then x2 derivative is not a function of the input and therefore 0, and that becomes our state equation. Finally, we can write our y of t in vector notation as a matrix multiplied by the vector x1, x2, and then plus a matrix multiplied by u of t. From equation 5, we notice that y of t is a function of x2 only, and therefore it will be written as 0 for x1 and 1 for x2. It's not a function of u, and therefore 0 for u. From this, we can obtain the state space representation of the system in terms of the state equation and the output equation of the system as represented in these two equations, and this becomes the state space model of our given circuit. That is one way in which we can represent the system's equation in state space form, and we can analyze it in a different format using another set of state variables. We take a different approach and obtain the state space representation of the same circuit. Now, from our first equation, we noted that E of t, which is our input, is given by the voltage across the inductor, which is DL, di dt plus, then the voltage across the resistor, which is Ri of t, plus the voltage across a capacitor in terms of its current is given by 1 over C, the integral of I dt. So the current the voltage through or across a capacitor is given in terms of 1 over C, the integral of I dt. You can call this equation A. From equation A, we also know that charge in terms of current is related by Q is equals to the integral of I dt. Charge is the integral of I dt, considering that I is dq dt. The rate of change of charge is our current, and therefore I can be defined as dq dt, or Q is the integral of I dt. We can substitute for this into equation A as follows. So we can write equation A as E of t is equals to L, and then di dt would mean we differentiate I and differentiate dq dt, which will give us the second derivative of Q as d squared Q dt plus, then Ri of t would mean that this is R dq dt, and then plus 1 over C, the integral of I dt. The integral of I dt is Q. We can write this as a second order differential equation in terms of charge Q as follows: d squared Q dt squared plus R over L dq dt plus 1 over LC. Q is the same as 1 over L E of t. You can call this equation B. From equation B, we have a second order differential equation in terms of charge: d squared Q dt squared plus R over L dq dt plus 1 over LCQ is equals to 1 over L E of t. We can choose the state variables such that x1 is equals to Q of t, and x2 is the first derivative of t. You can choose the two state variables, x1 to be Q of t and x2 to be Q derivative of t, from which we can write our x1 derivative will be equal to Q derivative, which is the same as x2. Q derivative is the same as x2. Also, x2 derivative is the same as Q double derivative, but Q double derivative from equation B, we can take Q double derivative, the subject of the formula, take all these terms to the right, and will form negative 1 over LC Q of t, but Q of t is x1 minus, then this becomes negative R over L dq dt, negative R over L, but dq dt is our x2, have that as x2, and then plus 1 over L E of t, 1 over L, but our E of t is our input, so we can write it as U of t. Then the output of the system can be written as Y of t is given by VC of t, VC of t which is the same as 1 over c, the integral of I dt, which is the same as 1 over c, the integral of I dt is q of t, which we can write as 1 over c, but we have defined our q of t to be x1, and therefore our y of t can also be written as 1 over c x1. From this set of equations, we can obtain the state space representation of the same system as follows. You can obtain the state space representation of the system as follows. So the vector x derivative, x1 derivative, x2 derivative is equal to the matrix A multiplied by x1, x2, our vector, plus the matrix B multiplied by the input u of t. So our x1 derivative is x2 from this equation. X1 derivative is x2, which means we can write this as 0, 1, 0 for x1 and 1 for x2. X2 derivative is negative 1 over LC. You can have this as negative 1 over LC, then negative R over LX2, so negative R over L for x2, and then the input part for x1 derivative is 0. It's not a function of the input, but it's 1 over L for our for our input. Then our output y of t can be written as a matrix C multiplied by the state vector x1, x2, multiplied by the state vector x1, x2, plus the matrix D multiplied by u of t. Our y of t has been defined as 1 over c x1. So for x1 is 1 over c, and for x2 is 0. It doesn't have the input part, which means d is 0. So this becomes the second state space representation of our given system when we take q, or the charge, and its derivative as our state variable. Based on this, we notice that we have two state space representation, or two state space model representing the same circuit. And one thing we can note is that state space approach is not unique. You can have the same system represented differently using different state space models, and all of them represent the same system depending on the state variables that we take in our design. And therefore, we can have different state space models representing the same system, and we can conclude that state space model is not unique for any given system. We can take another illustration of an electrical circuit. Okay, so we consider the following circuit. We consider this circuit. So we have resistor R1, capacitor C1, inductor L, capacitor C2, and resistor R2. Then you have a current I of T as the source current. The voltage is taken across resistor R2. The output is taken across resistor R2. So you can have this resistor shifted here. And this is our output. We are to determine the state space representation of the system, and we've been given that the values of R1 is equals to R2, which is 1 ohm. C1 is equals to C2, which is 1 farad, and L is 1 Henry. Okay, so we can indicate the currents in the network as follows. So there is this node and this node. This node and this node are the same nodes. So we call this node A and call this node B. The voltage here is V1. The voltage here is V2. Then the current I of 2 comes to node A, subdivides into these currents. So we can call this current I1, current I2, current I3, I4, and I5. Those are the currents we can have in our given network. Okay, those are the currents in the network. We can choose to analyze the circuit as follows. So we start with node A, or at node A. We know that the current that gets to node A, or the Kirchhoff's current law at node A, is I of T, which must be equal to what leaves the node, which is I4 plus I1 plus I2. That is the current at node A. This can be written as I of T is equals to I4 is the current through the resistor R1, which is supposed to be V1 over R1, but R1 is 1 ohm, so it will just be V1, plus I2 is the current that flows through capacitor C1. Current through a capacitor in terms of its voltage is given by C dV, but now the voltage is V1, so dV1 dt plus the current through the inductor, which is I2. It is good to note that the choice of state equation will depend on the voltage drop across capacitor C1, the voltage drop across capacitor C2, and the current through L2, the inductor L. That means we need V1, I2, and V2 as the state variables. And you notice that this equation is written with respect to V1 I2 as the choice of the state variables. We can rearrange this equation and write it as follows in terms of a first order differential equation as dv1 dt is equals to, then we divide both sides by c and take all the other terms to the left as negative 1 over c v1 minus 1 over c, but in this case our c1 in this equation, because this capacitor is C1, capacitor C1 is 1 farad. So we can simplify that as negative V1 minus, this one becomes negative I2 over C1, which means it's negative I2, and then plus I of t. We can write the node equation at node B as follows. Node B, call this equation 1. At node B, we have the currents that get to the node being I2 to be equal to the currents that leave the node is I3 plus I5. This can be written as I2 is equals to I3 in terms of the capacitor current as C2 dV, but the voltage is V2 dt, plus current through the resistor R2 will be V2 over R2, which will be V2 over R2. We can simplify these as a first order differential equation as dV2 dt is equals to dVt dt is equals to, we take this term to the left and we divide both sides by C2, but C2 is 1 farad, so it will be I2 minus V2, and we can call that equation 2. Next, if you are to analyze the voltage equation in this loop, notice the voltage V1 across the capacitor will be equal to the drop across the inductor and the drop across this capacitor. So we can write the equation in this loop 1. If we consider loop 1, we can write V1 is equals to the voltage across an inductor in terms of its current is given by L di, but that current is I2 dt plus V2. We can write this as a first order differential equation as di2 dt is equals to di2 dt is equals to, divide both sides by L, but L is 1, which means it will be V1 minus V2. You can call that equation 3. From equations 1, 2, and 3, we can obtain the state equation by defining the states of the system as follows. So we choose X1 to be V1, or the state X1 to be the voltage across capacitor C1. We can also define X2, we define X2, and define X2 to be the, it's not X2 prime, it's X2. Can define X2 to be the voltage across capacitor C2 as V2, and define X3 to be the current through the inductor, which is I2. Also, we know that our input I of t is our input U of t, and our output Y of t is equal to the voltage across the resistor R2, which is V2 of t. So those are the definitions of the given state variables, input and output of our circuit. Let's use equation 1 to 3 to write the state equation as follows. So from equation 1, I can write the x derivative, x1 derivative to be negative v1, which is negative x1 minus I2, which is x3 plus u of t. From equation 2, we can write, or from equation 2, we can write x2 derivative is equals to, so v dv2 dt is the same as x2 derivative, which will be equal to negative, start with v2, but v2 is x2, so negative x2 minus I2 is defined as x3 minus x3. Notice this sign is negative, this is positive. That's our second equation. From equation 3, di dt, our I is x3. That means this is the derivative of x3. We can write x3 derivative is equals to x3 derivative will be equal to v1. v1 is x1 minus v2. v2 is our x2. And this set of equation would constitute the state equation. Finally, we can write our y of t, which is our output, which is v2, but v2 is x2. So we can write this as x2. If we write the state equation and output equation in matrix notation, then we can obtain the state equations as follows. So from the state equation, I have x1 derivative, x2 derivative, x3 derivative as a vector, will be equal to the matrix A multiplied by x1, x2, x3. I can write this as negative 1, for x2 is 0, for x3 is negative 1. Then for x2, we have 0 for x1, negative 1 for x2, and 1 for x3. Then x3 derivative is 1 for x1, negative 1 for x2, and 0 for x3. Then plus the matrix B multiplied by our U of t, which is our input current. So x1 is the only term which is function of U of t as U of t. So this is 1. All the others are zeros. Similarly, we can write our y of t. We can write our y of t. Can write our y of t to be equal to a matrix C multiplied by the state vector x1, x2, x3. So the state vector is x1, x2, x3 plus d, but you notice no function of u, so d is 0. So 0 for x1, 1 for x2, and 0 for x3. And this constitutes the state space representation of that circuit. So that is how we model electrical circuits in state space representation. And note, we always take the state variables to be the current through the inductors and the voltage across the capacitors in our design or modeling of the system in state space representation. Otherwise, thank you so much. Next, I will be looking at the different ways or different forms of representing state space models, the canonical standards of representing the state space model. Thank you.